Electric field due to a disk along its axis. Okay, a disk. A disk is a collection of many concentric rings. Perfect. So modus operandi is clear. What do? Agenda is a disk with sigma. Sigma, lambda is linear charge density, sigma is surface charge density. I want to find out the field at point P, which is x away actually. All right. What do, guys? Imagine a very small ring of radius y and thickness some dy and charge dq. Now, this dq will be equal to what? Surface charge density into area of the very thin ring which you have taken. All right. What is the very thin area? 2 pi y dy. How did I get that? This is nothing but, guys, circumference into thickness. If you have a belt, the shaded part area is nothing but bigger area minus smaller area, obviously. But if you want a quick fix for that, it's nothing but the circumference into thickness. 2 pi y is the circumference, multiply by thickness dy. All right. So if I put this value, my dq expression is sigma times 2 pi y dy. Agreed? All right. So dE, following the formula for the ring, who's your element now? dq. But what is dq? Not a point charge, it's a ring. So whose formula will you use? Ring's formula. So dE is kx dq upon x squared plus y squared 3 by 2. All right. Put the value of dq. Okay. K sigma 2 pi y dy x upon x squared plus y squared 3 by 2. My hand is itching now because k is 1 upon 4 pi epsilon naught. And I have a 2 pi in the numerator. That pi and pi will get cancelled. I right now know itself. Okay. So let me hold on to the temptation for a while and then I will put it later. Can I add all the D's now? Are all the rings coaxial? Yes. Will all the rings which this disk is made up of will have field in same direction? Yes. What are you waiting for? Integrate. If you do that, y equals x tan theta. Sir, how do you know y equal to x tan theta each time? Hint. Whenever you have something minus x square in the numerator, the best thing to substitute is sine theta. Why? Because the hope is it will become 1 minus sine square theta and give you cos square theta. Whenever you have something plus x square, not minus, plus x square, always go for tan theta. Why? The hope is it becomes 1 plus tan square theta and gives you secant square theta. There you go. Y is x tan theta. If I do that, I actually shorten my integration. Look what happened. E becomes 2 pi sigma x upon 4 pi epsilon naught. I told you it will happen. And I put the value inside. And of course, when y is x tan theta, dy is x secant square theta. When y is 0, what is theta? 0. When y is r, theta is equal to some phi I am choosing. What is that phi? That final angle. It will come into picture. Don't worry. So, when I do that, my integration is sine theta d theta. Yet again, the proof of the fact that a polar or trigonometric integral is always better than an algebraic integral. Cos theta is by integration. Don't forget there is a minus sign and I have sigma by 2 epsilon naught 1 minus cos phi. Of course, what is cos phi? Cos phi is the total angle this disk is subtending. This one. This guy is cos phi. Sigma by 2 epsilon 1 minus cos phi. Perfect. For algebraic value of cos phi would be what? X under root x square plus y square, which that's cos theta actually. This is cos phi, which is x upon under root x square plus r square. And both the expressions are equally valid, your call. But if I were you, I would have remembered the first expression. Less messy, less effort, more efficiency, more and better result. Got it? So for a disk, the formula is sigma by 2 epsilon naught 1 minus cos phi. Where? Actually outwards. If the disk is positively charged. If the disk is negatively charged, actually inwards.